In this example, we're looking at a tank. The turret on the tank is rotating about a fixed axis at a rate of zero point 0.4 radians per second. That's a constant. The barrel is being raised at a constant rate of zero point 0.4 radians per second. And at the same time, there's a shell which is being fired. It's got a muzzle speed of 200 feet per second relative to the barrel. We have an observer that's on the barrel. What we want to do first is find the omega and the alpha for that observer, and then two, find the acceleration of the shell as it leaves the barrel there at P. So let's write down what we're going to use here. We're going to put this observer on the barrel. We're going to attach lowercase xyz on the barrel, and then have a second set of axes which are going to be fixed. Big XYZ is going to be fixed onto ground. In other words, it's fixed. So the first thing we need to do is find the angular velocity of the observer. Two components. Big omega about the fixed axis of J. There's a theta dot component which is about the moving K axis, and that's a plus. Alpha, that's the angular acceleration, so that's d omega dt. Differentiation, omega dot J, omega J dot, plus theta double dot K, plus theta dot K dot. Keep in mind that this is a fixed axis. This is a moving axis. So that says since J is a fixed axis, J dot is a 0. It's given that omega is a constant and that theta dot is a constant. So what we have left is a theta dot K dot, that's omega cross K. So it's theta dot, where omega was big omega, big J. Theta dot small k crossed with small k. Any vector crossed with itself is a 0. So what we're left with is theta dot omega big J crossed with small k. We want to find that when theta is, are we given an angle here? It looks like not, so we'll just say in general for this angle of theta. So for that, I've got, if I look at this thing from the side, I got I like this, J like this, big J. The angle theta is like this. So this theta is there. If I project big J onto small I, from here you see that big J is equal to cosine theta small I plus, oops, that's a sine theta, isn't it? Sine theta small I plus cosine theta small j. So this becomes theta dot omega sine theta I cosine theta j cross k. So what I have here is a j cross k we know is a plus I, so this is theta dot omega cosine theta I cross k is a minus j, so this is minus theta dot omega sine theta j, like that. So that's our alpha vector. Our omega vector, just to be clear, is going to be big omega big J, so that's sine theta I plus cosine theta small j plus theta dot k. So that's our omega vector, that's our alpha vector. Same kind of thing we've been doing in most of our examples. But now we're asked to find the actual acceleration of of the shell as it exits the barrel there at NP of the barrel. So what I will do is I'll write down the acceleration of P using the moving reference frame equation. You got 5 terms, as always. Like that. And let's see, the only thing that's going to drop out here is that it says that the shell happens to have a constant muzzle velocity of 200. So the only thing that's going to drop out is here. Our observer is going to see a shell moving along a barrel with a constant speed. The other terms we need to have, I'll write these out here. AO, that's the acceleration of this point right here. And let me correct myself here. I can't use this point O because keep in mind that that point has to be on the same moving frame as our observer. So I made a mistake here. I should have been calling that C. So let me go through and correct that. This should be C. It's got to be same point or a point on the same moving frame as our observer. O does not work, C does. So this has to be a C. What is the acceleration of O? Well, if you look at this thing from the top, O is moving on a circle. C is moving on a circle about O, radius of R. So it's moving at a constant speed, but it still has a centripetal component here for that. So AO is going to be equal to the speed, which is R omega squared divided by rho, which is R, and that's going to be pointing in the minus I. Because this, looking at from the top, this is I, big I, and this is big J. Or not big J, but big K. So we need to do some more projections. This was small I, small j, and now we need to project big I onto there. So this angle here was a theta. So we project, when we bring this minus sign on the outside, it's going to be an R omega squared. And the I vector, if I project that on the small I, it's a cosine. It's a minus sine theta small j, like that. The alpha vector, we have that. The R vector, let's write down that one. R vector from P with respect to C is simply going to be along small I, and it's going to be at a distance of L, like that. What else do we need? Omega, we have that. VREL, let's write down that. V, it's going to be the muzzle velocity in the small I. And mega vector, we've got that. R, got that. So we'll just simply say substitute into above equation. all the thinking has been done in setting up these terms. It's just a matter of algebra in doing the alpha cross R's, omega cross V rels, and omega cross R's. So, long problem. Um, what we had to first recognize is that if we wanted the omega for the barrel, it had two components. One about a fixed axis of big J, and one about a moving axis of K. We did our usual differentiation of omega to get the alpha vector. We had to do a coordinate transformation to transform big J over to small I and J. And then we used the moving reference frame equation to predict what the acceleration of that shell is when it leaves the barrel. And the thing here which I goofed on was that we have to be very careful. We reference back to a point on the same moving frame as our observer. My original choice of O didn't work because it's not on the same rigid body as our observer. I chose C, and with C we had to do a little bit of work here to find the acceleration of that point, but not too bad, knowing it's traveling on a circular path with a constant speed.